Hey everyone, welcome to Magnitude. This is Manak Dasgupta, and today we have came with a new video of the semiconductor series. And on this video, we are going to discuss about the energy levels, energy band, conduction band, valence band, and the most important forbidden band gap. And at the last, we will also discuss about the difference between the conductor, semiconductor, and insulator depending upon the energy band diagram. If you have not watched our previous videos, then do watch it. In the last video I have also discussed about the free electrons, holes, and also the motions. So do watch all these videos of this series. I will give the link in the description box. And if you are new to our channel, then please subscribe to our channel and hit the bell icon to get the latest updates of our channel. So not wasting much time, let's begin. So, while understanding the energy bands or the energy levels, we should know this thing that in an isolated atom, the energy of an electron depends upon the orbit it is revolving. Means the energy of an electron is always dependent on the orbit which it is revolving. But you should make one thing very clear, that this is mentioned for only isolated atom, not for the atoms in crystal. This thing is only valid for an isolated atom. One more thing is also important, that is, we know in case of isolated atom, in case of isolated atoms, in case of isolated atom, we know that the energy levels are always discrete, for isolated atoms. In case of isolated atoms, the energy levels are always discrete. Means what happens, I will show by giving you an example also afterward. What happens, this all things means in isolated atoms the energy of an electron depends upon the orbit. In case of isolated atoms, the energy levels are always discrete. All these things are only valid for isolated atoms, for these isolated atoms. But you just tell me one thing, that where you will find these types of isolated atoms? Do you get the isolated atom anywhere? Means if you can find where I have found this amount of silicon, this is an isolated atom of silicon, can you find this thing? Definitely no. You cannot find this type of isolated atoms. You always find a crystal of silicon or a crystal of sodium. Means all these type of elements are found in a crystal form. Yes, I know, while making periodic table or while discovering new items, we find in an isolated condition or we experiment them as an isolated condition, but in real life we always find them in a crystalline format, or in a, not in crystalline, actually in a form of a crystal. Means they are not in a form of an isolated structure. So now we will understand that what happens when a crystal forms. So as I have said that in isolated atoms all the energy levels are discrete, but in case of crystals this is not possible. So you know that sodium. So in sodium we represent it by Na. So the atomic number of sodium is 11. So the electronic configuration will be 1s2, 2s2, 2p6, 3s1. This will be the electronic configuration. So how we can draw this thing? We can draw it by, this one will be 1s2, 1s line, this one will be the 2s line, this one will be the 2p line, and this one will be the 3s line. So in case of isolated, when this Na is in an isolated format, in that case all these energy levels, these are known as energy levels. These are known as energy levels. All these energy levels will be discrete, means a single line will be there. In case of the first line, it is minus 13.6 electron volt. So this means the first line is 1s line, this one will be exactly minus 13.6. So In case of isolated atoms, it will be always discrete, but this thing doesn't happens for a crystal format. When this sodium atom is a crystal format, this thing doesn't happens. So what happens when it is in a crystalline format? So let's see. The same thing but slightly different. What happens? You will find it. The 3s line, suppose we are drawing the 3s line here, the 2p line here, and the 2s line here, and the 1s line here. What happens? This doesn't remain a discrete format. This become a band. So why this become a small band? So I will consider this thing first. So why this become a band? In case of crystalline format of the atoms, what happens? All the atoms takes a unique position. Means what happens when the atom comes in a crystalline format, they interact with the adjacent atoms. As I have described in the first, in case of silicon, as I have described that thing, they always interact with the adjacent atoms. So when an atom interact with its adjacent atom, what happens? The electrons, the outer electrons, they interact with the electrons of the adjacent atom and also interact with the nucleus of the adjacent atom. So of this, when this thing happens, what happens? The energy level of these electrons, when the atom is in crystalline format, the energy level of these electrons slightly changes. What happens? They slightly increases from the exact energy level or slightly decreases from the exact energy level. So what happens when they are isolated? They should be in this discrete line. This is the line which they should remain. But when they are in crystalline format, what happens? This not remain as a single line. As I have said that the energy level slightly increases, so sometimes it became like this, or like this formats. And I have also said that it sometimes decreases also. So what happens? It sometimes become like this. So what happens actually, the outermost electron, 3s1, when this 3s1, this one is the outermost. So the outermost electron always interact more with the adjacent electrons of the adjacent atom. And the inner shells, they generally interact less, and the first cell interact very little. More the outermost shell interact the most. So do you think that this part now actually look like a energy level? This single part are all energy level, but when this whole thing becomes a bunch of energy levels, then we call this part as energy band. Then this part is known as energy band. Each single line, discrete line, is known as energy level. But when we are looking like this, then it is known as energy band. And there is a very slight gap between each of them, because this total part is within 1 electron volt, and there are more than 10 to the power 23 number of lines, number of energy levels. So it is very small gap between them, and this part is known as energy band. So now we will discuss what is conduction band and what is valence band. So before discussing that, I would like to say that we have found that silicon Si have 4 valence electrons. So this type of electrons which are valence electrons, they are generally found in the valence band. And the conduction band is that band which is just above the valence band. So let us consider the topmost shell of any electronic configuration, and we will see that the band, so what is valence band? We will say that the band which contains all the valence electrons in it, means the band which contain all the valence electrons is known as valence band. And what is conduction band? The band which is above valence band is known as conduction band. The band which is above the valence band is known as conduction band. So let us more detail discuss on this topic, that what is the difference between valence band and conduction band. So what happens in valence band and conduction band? In valence band, all the energy levels are due to these valence electrons, and in a conduction band, all these energy levels are due to the free electrons. Due to the free electrons. Actually, what happens? All the electrons here present here are valence electrons. So when these electrons, they actually move to this band, they become free electron. As I have said earlier, that when the electrons come out of their shell and they become free, they actually come out of their valence band and they go to the conduction band, and hence they become free electrons. So all the energy levels present in the conduction band are due to the free electrons, and all the energy level present in the valence band are due to the valence electrons. So this is one important point. Another important point is valence band does not participate in the conduction of electric current, or in the conduction of the electrons, or the motion of the electrons. This valence band does not conduct electricity. They doesn't participate. But all this participation in the formation of electricity or in the motion of the electrons is due to this conduction band, because in the conduction band there are free electrons. Okay. Another important thing is, there is no mandatory condition that always there will be free electron in valence band. We will see afterward that in some cases there are free electrons, and in some cases the conduction band is very far from the valence band, so free electrons cannot move there. That we will see afterward. So these are the basic differences between the valence band and the conduction band. Now we will move to the next topic, which is also a very important topic, and various number of questions come from this topic. That is, we will describe what is forbidden energy band gap. So let us first say that this band gap, the energy level of this band gap is defined by EV, and the energy level of this conduction band is defined by EC. So the gap between the valence band and the conduction band is known as forbidden energy band gap. I have written a short form, it's known as forbidden energy band gap. So if anyone asks you to define what is forbidden band energy band gap, then you will definitely say that forbidden energy band gap is the gap between the minimum energy level of EC, means the energy level of conduction band, and the maximum energy level of EV, that is the energy level of valence band. Many of the books or somewhere it is written that forbidden energy band gap is that gap which is between the valence band and conduction band. Although it is correct, but I would like to prefer that you must say that the minimum of EC, means the energy level of conduction band, and the maximum of EV, the energy level of the valence band. The difference between these two is known as forbidden energy band gap. Even this forbidden energy band gap is defined by EG. So if anyone asks you what is the formula of EG, you can definitely write that EG equals to EC min minus EV max. The minimum of energy level of conduction band minus the maximum of energy level of valence band. So by this thing we know what is forbidden energy band gap. So this topic is up to here. Next we will move to the most interesting part, that is the difference between the conductors, the insulators and the semiconductors, depending on this band diagram. So how we can judge which is conductor, which is semiconductor, which is insulator, by just seeing or by just describing how the band gap or this energy bands work. So let's move to that part. So what happened in case of semiconductor? In the case of semiconductor, the conduction band and the valence band lies almost near to each other. So what happens, the electrons from the valence band, if these are the electrons from the valence band, they easily move to the conduction band. When required, they can easily move to the conduction band. So this thing happens in case of semiconductors. But now we will see what happens in case of conductors. So in case of conductors, we know that in conductors the number of free electrons are much greater. Means they have a huge number of greater amount of free electrons. So what happens in case of conductors? In case of conductors, the valence band is something like this. I am representing valence band by VB, and the conduction band just overlaps the valence band. So here is a overlap of this valence band and the conduction band. So what happens, the electrons of this valence band, they can easily move to the conduction band. Means those electrons who are present in the valence band, they can easily go to the conduction band because they are overlapping, they are connecting each other. So here the forbidden band gap is 0. No forbidden band gap is present in case of conductors. In case of semiconductor, a small forbidden band gap is also present. So what happens in case of insulators? In case of insulators, if this is the valence band, then the conduction band will be somewhere like this. So there is a huge difference between the valence band and the conduction band. So if any electron is present in the valence band, they don't have enough energy to move to the conduction band. They cannot move to the conduction band, hence they don't have any free electrons. So the energy conduction in case of insulators is not possible, and hence it has a very large forbidden energy band gap. So these are the basic stuffs. One more thing I would like to mention that I have not mentioned earlier or I have missed, that is electrons are the negatively charged particle. So we will consider the holes as the positively charged particles. As I have said that holes are just opposite of the electrons, means the deficiency of electrons in a particular place is known as the holes. So electrons are negatively charged and the holes are the positively charged. So this tutorial video is up to here. In the next video we will move forward to the types of semiconductor, the different parts of the semiconductor. So if you like this video, then don't forget to give the like button and share the video with others, and hope it will be beneficial for all. Thank you everyone for watching this video.